Hello, I am Niko Mäkitalo from University of Helsinki, and me and my team are presenting our paper, bringing WebAssembly up to speed with dynamic linking. And here is our team. So Risto Mikkola.
Hello.
Polios Dauprais.
Hello.
Viktor Pankowski.
Hello.
And Tommi Mikkonen.
Hello everyone.
So here's the overview of this presentation. First, we start with the motivation, what brings us to this research topic. Then we talk about our long-term vision, what we are trying to achieve. Then we discuss about the architecture of the implementation. Then we continue with an example application and demonstrator video that shows the current implementation. Then we evaluate the approach and discuss how well it performs in contrast to other solutions. And then finally, we conclude this presentation.
Okay, let's start from the motivation. WebAssembly was initially designed to be used in the context of the web. And as such, although I have personally been working in web programming for over 15 years by now, I was completely overlooking its possibilities. When I started to look that into a couple of years ago, it still looked like an appendix made to the browser so that you could increase the performance to near native speed, do some code obfuscation, but it fundamentally was a piece of the browser. So it would use as much memory and it would have a bunch of similar limitations as the browser has. Now, during the recent years, or maybe the recent year 2020, it seems that the people have noticed that the WebAssembly has really a lot of promise outside the browser. So there are plenty of papers about the using WebAssembly for IoT services, for serverless computing, and the likes. However, nobody has been paying that much attention into the fact that once you start using WebAssembly in different contexts, you also need to think about memory, performance, user experience, and many other things that are common in diverse systems. And hence, you cannot rely on everything being done statically like you can often do things in the context of web pages. Instead, you need some more dynamic features that help you to do things in pieces and as you go, instead of loading everything in one shot in the beginning.
So the figure shown on the slide presents the envisioned system, and we foresee that the implementation is capable of initially starting with the base module. The base application is then built progressively by retrieving additional modules on demand from external repositories, compiling them in a streaming fashion, and finally linking them to the application. The implementation can go even a step further by predicting when to load additional modules based on some additional analysis. So whenever there is functionality needed, the module would be ready to be used. The part of the envisioned system we implemented is the dynamic linking mechanism, which enables us to split WASM applications into smaller pieces that are assembled during the execution. The base module acts as a starting point of the application. Upon its invocation, it prepares the runtime with all the necessary setup steps so that the implementation could be capable to dynamically link the retrieved modules. For example, creating different components such as global memory or global table that would be used by subsequent WebAssembly modules. Compared to the conventional monolithic WebAssembly applications, our implementation creates the possibility to increase startup time significantly, as only the initial base module is needed at the very beginning of the execution. Similarly, It is not unusual to have applications that carry code which is completely unused throughout the whole lifetime of the application. The system helps to think about the application's architecture and build applications by only loading the necessary code. Also, it lays the foundation for further development, allowing it to load context-specific modules. In addition, having only the necessary modules improves memory consumption. However, without the capability to unload modules, memory consumption benefits are present only until all modules are loaded. The architecture shown in the figure is fairly simple. The host application acts as a runtime, providing an environment for a WASM application to run in. It maintains global objects to keep information crucial for dynamic linking mechanism accessible at all times, such as host functions, DLOpen, DLSym, and DLError that enable the dynamic linking process. WebAssembly virtual machine embedding API that enables to access modules, components at ease and compile them. And host functions are available also to other WebAssembly modules in case they need to load additional functionality.
So next up is our dynamic linking demonstrator application. It is an Android application that uses our dynamic linking implementation to load and link modules. In the demo video, we load and link image manipulation filters to edit an image, as well as demonstrate some other features of the runtime. So right at the beginning of the video, we wanted to emphasize that the demo is actually running on a real Android phone and not, for example, on an emulator. So on the right you can see that this phone screen is not an emulator window, but instead it's a screen mirroring software. And here you can see footage of the physical phone screen, and you can see that both the mirroring software and the phone screen sync up. So in the beginning, the main module is loaded and its initialization function is run. The initialization function sets up the GUI elements as well as the callbacks for the buttons using host functions. The dump button triggers debug prints into the console. The output shows which modules are loaded and which functions are linked from those modules. The Say Something button loads and links in a module which changes the text view above it. Here are the host functions used to create it. The Create button function creates the button on the Android side and returns a handle to it. The Register on Click function takes in that handle and assigns a callback function from the module to that button. The callback for this button loads in a module called Android Chatbot and links a function called WriteMessage and then runs that function. The actual loading and linking is performed similarly to Linux, for example, by first loading the module with DLOpen and then linking a function from it using DLSym. Here's the code of the side module. The WriteMessage function takes a handle to a text view and writes one of the pre-written messages in it. What's notable here is that the side modules can also import host functions. In this case, the modify text view host function is imported in order to write the messages. And now the dump button shows the previously loaded module and the function linked from it. The error demo button demonstrates our error handling. The application doesn't crash when an error occurs. Instead, DLR can be used to retrieve the error message. Here we use the text view to show the error for demonstration purposes. In this case, the error was an attempt to load a non-existent module. The dump button shows that no new modules were loaded. Now we load an image to the black canvas area using the load image button. In this demo, the image is embedded into a module and a function in the module is used to load the image into linear memory and then into the canvas. In a future implementation, a host function could be used to load the image instead. Here is the redraw function that updates the canvas. The value of each pixel is copied from an image buffer into the bitmap using the modify bitmap function. So this is the previously mentioned setup function for the image module. It copies the embedded image data into the image buffer, which was also used in the redraw function shown before. Now that we have an image to edit, let's invert its colors using the invert button. And now we can see that the image is inverted. Here's the inversion code. It also operates on the same image buffer seen before. Now let's grayscale the image. The grayscale function also operates on the same image buffer as well. What this demonstrates is that data can be freely passed between multiple modules because all of them share the same linear memory. Here we see for the final time all the modules that we have loaded and all the functions we've linked. At the beginning there were none, and as the demo progressed, more of them were added in right at the points they were actually needed.
To evaluate our system, we compared a modular application with a monolithic WASM application. The applications implement the same program consisting of thousands of functions. The modular application has a small base module and 10 modules where the functions are distributed evenly. We measured the startup time of the applications, different configurations of execution, and the overhead of loading modules and calling their functions. The modules were compiled with mscripten to keep content similar between the applications. Optimizations were left out. Here you can see the evaluation of the startup. Operations such as reading the binary, compiling it, and instantiating it take time and resources when starting up a program. All of these can be reduced through dynamic linking, as indicated by the startup measurements. The base module contains only the bare minimum to get the application started, while the monolithic application has to be loaded entirely. When measuring the time and memory consumption of performing an action, the modular application is able to load only the modules containing the necessary code to resolve the necessary function. As a result, it performs the same action as the monolithic application, but uses less memory, space, and time. When the modular application loads all of the modules and resolves one or all of the functions in the modules, then the binary size and execution time are only slightly higher. However, memory consumption is much higher due to the additional data used by the dynamic linking implementation. In the runtime overhead measurements, a module containing a single function is linked using DLOpen and DLSym. Even though DLOpen does compilation, it is still able to run in less than a millisecond for our small module. Linking of a function with DLSym takes considerably less time, only 34 microseconds. On average, calling a function within a module takes 3.5 nanoseconds. This is what a function call in a monolithic application would take to execute, and it is used as a baseline. On average, calling the same function linked with delsym takes 9.8 nanoseconds, which is almost 3 times as long as the baseline. During instantiation step of linking, modules can import functions from already loaded modules. Calling the same function through an import takes 4.8 nanoseconds, which is only 40% slower than the baseline. The evaluation has several limitations. For the runtime, our work is largely affected by the underlying WASM runtime. WASM time as well as other runtimes are progressing quickly, so this is a moving target. Compilers, on the other hand, cannot currently generate dynamically linkable modules outside of the browser, or the support for it is experimental. Additionally, streaming compilation of WASM modules appears to be a work in progress for the runtimes we have experimented with. For WASM, while the current WASM specification allows the creation of execution time dynamic linking, there is a proposal for module linking called module types that can simplify and improve the implementation even further. The proposal suggests adding load time dynamic linking to the WASM specification. While this would not implement execution time dynamic linking, it could require runtimes to implement features that benefit execution time dynamic linking. Our implementation was created for research purposes, and as such, it has numerous weaknesses.
So here are the conclusions for this presentation. So we first started with the motivation for the paper. We have explored the use of WebAssembly technology for building cross-platform modular applications that can also run outside the browser. We believe that the combination of WebAssembly and the execution time dynamic linking has actually the potential to revolutionize the way how cross-platform software can be developed. With our approach, it is possible to create an ecosystem. Components and these modules can be developed independently and shared and combined to create various applications. We also presented the proof of concept implementation that builds on previously introduced WASM concepts, mainly on WASM time. The functionality to load WASM modules and link desired functionality during the execution was also presented.
And that's all, folks. Thank you very much. I'm now ready for whatever questions you might have in your mind. Thank you.